So often these rates are related over time. So as I showed with my circle graph here, that point is moving, the X, Y value are changing, and they're each changing in a way that keeps the point on the circle, right? The rate at which X is changing, the rate at which Y is changing are keeping it bound to the circle there. So, but it's not always time. There's other things that go on. So suppose I have a balloon. So here's my little balloon. There's the nozzle I can blow it up in. And then I start blowing air into it, right? So we're going to blow air into the balloon. Now, instead of blowing it by hand, maybe I'm going to use an air compressor that's going to blow it up for me. And that air compressor is going to blow in at a steady rate. And as that happens, right, the balloon's going to get bigger and bigger and bigger. Now, for simplicity, we're going to suppose that this balloon is a sphere, perfect sphere. And I know the volume of a sphere is 4/3 times pi. Come on, there you go. Times the radius cubed. All right, so just multiply 4/3 times pi times the radius cubed. That tells me the volume here. Now my air compressor is blowing air in, and let's suppose that it's blowing air at a rate, changing the volume over time, 1,000 cubic centimeters per minute. Not too fast, it's blowing kind of a slow rate there. So as that more air goes in here at a steady rate, this gets bigger and bigger. Well, as it gets bigger and bigger, that radius is getting bigger and bigger and bigger and bigger. So if I know how the volume changes, can I predict how the balloon gets bigger, how it appears to grow? And what we see really is like the radius of the diameter growing. We're going to focus on the radius here. The catch is just implicit differentiation. So we know the volume is changing over time, and because the volume here is related to the radius must be changing along with that. And because we know about implicit differentiation, we can differentiate each side here with respect to time. So we're going to take the derivative of the left side with respect to time. And from our work with implicit differentiation, we know that should be equal to the rate of change on the right side with respect to time. So I don't want to write that in there quite yet. Let's just put a box for it. So we're going to differentiate that side with respect to time and this side with respect to time. And that's not too bad. The derivative with respect to time of volume is just dv dt. Nothing magical there. Just drop those brackets. And we know that that's a constant here, right? So we'll come back and plug that in a minute. On the other side, 4/3 is a constant and pi is the constant, so they just hang out as constant multiples. And then I have to take the derivative of r cubed. Well, on its own, its derivative is 3r squared. But we know r is a function of time, right? R is changing over time because we're blowing air into the balloon. So we have to multiply, according to the chain rule, by dr dt. So now we have a new equation that relates how the radius changes over time to how the volume changes over time. So now I can answer that question. So I'm going to solve this for dr dt. But first, we know it's always a good idea to clean things up. And the 3's divide out. And that's about it. So let's rewrite that. So we have that dv dt, the rate of change of the volume, is related to the rate of change of the radius by 4 pi r squared. And I just want to point something really cute out here. This came from the fact that the volume of a sphere is 4/3 pi r cubed. And some of you may remember from your past life in math that the surface area, let's call that SA, of a sphere is 4 pi r squared. And what do I have right here but the surface area of that sphere? And the way I like to think about that is imagine a sphere. So here's my best picture of a sphere. I can kind of see through it there. And I paint the sphere. Now, paint has volume, right? There's this can of paint, and I start slathering it around. Now, that paint has thickness. So when I paint this, what do I get? Well, I get the surface area, essentially, which is that 4/3 pi r squared. But since the paint has volume, then the amount of paint that ends up on my sphere is going to be roughly 4 pi r squared times the thickness of the paint. And if you think about it, doesn't the paint extend the radius, right? The sphere just got a little bigger because I painted it. So the thickness of the paint would be my dr. And that's what I have here, is a little chunk of volume of paint around that, which is kind of, in this case, it'd be a little chunk of air that's on the inside of the sphere that made that sphere just a little bit bigger, that balloon a little bit bigger. But that's all changing over time. So I thought that's just a beautiful relationship between the surface area and the volume, and how that relationship between changing volume and changing radius work. It's basically a little chunk of surface area, or a thin, surface area surrounding it. All right, we want to solve this for dr dt, which is pretty straightforward. We just divide by 4 pi r squared. So I'm going to rewrite this in the other order. Dr dt is equal to whatever dv dt is divided by 4 pi r squared. And at first, what I see here is I would have to know r to continue this calculation. So I'd have to pick a point when the radius is some amount. But dv dt is always constant here, right? I pick that to be 1,000. So as long as that stays constant, then the rate of change of the radius is 1,000 over 4 pi r squared. And I just want to think about the graph of that for a second before we plug in a number. So let's go back to Desmos here. And let's bring up a new Desmos. I think I might save that one. Desmos calculator. So I want to look at, let's call it d for derivative. We have to use x here. And mine is a fraction with 1,000 in the top, and then the 4 pi, and I'll use x squared here. So that's my equation. And let's rescale that just a little bit. Go up a bit higher. Let's see, y-axis. Why don't we go up to 20 centimeters? Not too bad. So what this is the rate of change of the radius. So here on the bottom axis, that's my radius. Let's get a screenshot of that to scribble on. Ooh, wrong button. Whoa, what just happened there? There it goes. So what are we looking at here? So I'm graphing this right here. My rate of change of the radius is a function of the radius. So I'm graphing r along the x-axis and dr dt along the y-axis. And what this shows me, and again, one thing we want to keep in our minds here is the rate of change of volume is always the same. So rate of change of volume is constant. It's always 1,000 cubic centimeters per minute. It's constant. And if the radius is small, that 1,000 cubic centimeters of air that went in that minute, right, that makes the radius a lot bigger. There's a much bigger change for a small r. So when r is relatively small, like what am I at here? I'm at around 2.5 centimeters for R, I get the radius is changing by 15 centimeters per minute. However, later when the balloon is much bigger, so it's got a radius of 10 centimeters, I get a much smaller rate of change of centimeters per minute because all of that 1,000 cubic centimeters got spread out in this bigger balloon. So smaller balloon with that volume, I see a big change in the size of the balloon over that minute. But when the balloon is bigger, that change is less significant because there's more space for that air to spread out in. Is kind of the way to think about that. So if somebody said, okay, well, what's the rate of change when the radius, the radius is equal to 5 centimeters, then I just plug that in here. dr dt evaluated at r equals 5 would just be 1,000 over 4 pi times 5 squared. And we could plug that into our calculator. Actually, we could do that one on our head. Let's see, 5 squared is 25 times 4 is 100. 100 goes into 1,000 10 times. I guess we can't do it all in our head. Whatever 10 over pi is. Pi is about 3. 3 goes into 10, a little over 3 times. So maybe that's like 3.5. Let's check it on a calculator. So if I plug in 5 there, what's the rate of change at 5? Okay, I was a little bit off, 3.2-ish centimeters per second. How do I know it's centimeters per second? That's a good question. So this is about 3.2 centimeters per second, minute, sorry, minutes. Well, my numerator is centimeters cubed per minute. And my denominator, I took 5 centimeters and squared it. So now I have centimeters squared in the bottom. And so that cleans up. Centimeters cubed over centimeters squared is centimeters. And I should do MIN, not to confuse with meters. So that's definitely centimeters per minute. And it ought to be centimeters per minute because I'm looking at a change in the radius, which is measured in centimeters, over a change in time, which is measured in minutes. So at, again, about 5 centimeters, I can see I get a little more than a rate of change of 3 centimeters per minute, where when it was around, let's say, 2 centimeters, according to the graph here, it looks like at 2, it's a little over, what, 16, 17, 18, 19 centimeters per minute-ish, when the radius is equal to 2 there. So I can answer lots of questions, assuming the volume's constant. Now, if the volume changed at some functional rate, then I still can figure that out because I know the relationship between the change in volume and the change in radius over time. All right, let's try another problem.